All right, I'm going to walk you through a modern physics problem. In this problem, a photon collides with an electron. Anytime a photon collides with an electron, this is referred to as the Compton effect. All right, so this is what we've got. In this problem, a photon moving this way hits an electron, which is at rest. And then at the end, the photon bounces that way, and the electron moves this way. Direction is important with collisions. What do we know? The photon of the incident wavelength, is 2 × 10⁻11 that strikes a free electron of a certain mass. All electrons have the same mass. The mass of an electron is on the front page of the equation sheet, 9.11 × 10⁻31 kilograms, which is at rest, as shown above. After the collision, that's important. Delta, lambda is important. We'll go over that in a second. And reverse direction, as we said over here. Determine the energy in joules of the incident photon. Okay. Energy of a photon equals HF. HF, we don't have F. Instead of F, you have lambda. So we can relate this because the velocity of a wave equals frequency times wavelength, and it's light, so we get that. Frequency is equal to c over lambda. Take that, plug it into there, you get E equals hc over lambda. So the energy of the incident photon will be 6.626 times 10 to the minus 34th joules seconds, multiplied by c, 3 times 10 to the 8th meters per second, divided by the wavelength, 2 times 10 to the minus 11th meters. You do all that arithmetic, and you should come up with 9.939 times 10 to the minus 15th joules. There's the answer to the first part of the problem, 9.39 times 10 to the minus 15th joules. Now they want to know the momentum of this incident photon. Momentum. You're not given momentum. You are given energy or wavelengths, but there's an equation on the reference tables that equate the two. You get wavelength equals h over momentum. Determine the magnitude of momentum, or you can rewrite this as momentum equals h over wavelength. So basically it's 6.626 times 10 to the minus 34th joule seconds divided by the wavelength. The wavelength of the incident light was 2 times 10 to the minus 11 meters. You do that math. The momentum is 3.313 times 10 to the minus, I forget the number. Got to do the math. 6.626 second E negative 34 divided by 2 second E negative 11 negative 23rd minus 23rd kilogram meters per second. So there's your second answer. That's the momentum of the initial photon, incident photon. So there's those two parts there. Now what's going to happen here? Indicate whether the photon wavelength is increased or decreased by this interaction. Let's think about the collision. What's going on here? Right? Any collision. Momentum before equals momentum after. The momentum before, you've got a photon plus an electron. Afterwards, you've got a photon and an electron. Momentum's got to be conserved. If the electron initially has no momentum, this thing is at rest. Momentum equals 0. And this thing's moving this way and this thing. So these things both have momentum. The initial momentum of the photon gives rise to all of this momentum. If the electron takes momentum, it's got to get the momentum from here. So it's going to take momentum away from the incident photon in the collision. Here is your explanation. Since the relationship is like so, I don't know why that keeps on happening there. Since the relationship is like that, if a decrease in momentum causes an increase in wavelength. This is your explanation of reasoning. Right, these two things. And the momentum is going to be conserved in the collision, and since the electron comes away with some momentum and it had 0 to start with, the momentum gained by the electron will be equal to the momentum lost by the incident photon. So the momentum will be increased by a bit. Sorry, the momentum is decreased, and there is an inverse relationship between momentum and wavelength. So the wavelength of the photon will be increased. Now comes the hard part of the problem. Determine the magnitude of the momentum of the acquired by the electron. This becomes a little tricky math. And you were told the change of the wavelength of the photon is 2h mass the electron times c. Change in. Anytime you have change in, delta, it's always final minus initial. Always. So with the wavelength final minus the wavelength initial of the photon. That's what delta means. Always final minus initial. You were told the initial. The initial is 2 times 10 to the minus 11th. You were told this. You got to find the final. Let's see. Right? So we can bring this to that side of the equation, and you're going to get, you can rewrite this as the final equals that plus lambda initial. So 2h over mc plus the initial is 2 times 10 to the minus 11th meters equals the final. So do all this math. 2 times Planck's constant. 2 times 6.626 times 10 to the minus 34th joules seconds over 9.11 times 10 to the minus 31st kilograms times 3 times 10 to the 8th meters per second plus 2 times 10 to the minus 11 meters. You do all this arithmetic and let's see what we get. 2 times 6.626 negative 34th gives you that number. Divide that number by 9.11 negative 31 kilograms divided by C3 gives you that plus 2 times 10 to the negative 11th gives you that. So you get the new final wavelength to be 2.48, we'll go 2.485 times 10 to the minus 11 meters. We want the momentum acquired by the electron. What we need to do, we know the momentum before the collision has got to be the same as momentum after the collision. So what's this momentum going to be? We have to convert this into momentum. All right, so converting that into momentum, wavelength or momentum equals h over wavelength. So let's take this, I'll give myself some more space. Momentum equals h over wavelength, so we'll go 6.626 times 10 to the minus 34th joule seconds over this wavelength, 2.485 times 10 to the minus 11 meters. The momentum of the photon afterwards will be 6.626 negative 34th divided by, let's go, type the right numbers in, 2.485 times 10 to the minus 11th gives us this number of 2.666 times 10 to the minus 23rd kilogram meters per second. All right, so this is the momentum after the collision, of the bit of light after collision. So going back to the beginning, we have the momentum before equals the momentum after. The momentum before is just the momentum of the light incident. That was a 3.31. That plus the electron, which was 0, pretty much ignore that, equals the momentum of the bit of light after plus the momentum of the electron. Now, this is important. The thing switches direction here. So this thing was moving to the right. This thing is moving to the left. This thing is moving to the right. We have to make this, because it's going that direction, we're going to make it negative. So what do we end up with? We started with 3.313 times 10 to the minus 23rd kilograms equals a negative 2.666 times 10 to the minus 23rd kilogram meters per second plus the momentum of the electron that way to the right. We have to bring this over there, and we'll get the momentum of the electron to be the momentum of the electron after the collision equals 3.313 times 10 to the minus 23rd, that should be kilogram meters per second, kilogram meters per second plus 2.666 times 10 to the minus 23rd kilogram meters per second. So the momentum of the electron afterwards equals, we'll add those two numbers up, 3.313 negative 23 plus 2.666 minus 23 gives us 5.979 times 10 to the minus 23rd kilogram meters per second. And it is moving that way, so we'll call it positive.